AP Calculus. We are looking at related rates. This first video is going to be an introduction of just getting our feet wet of how to take the derivative of different formulas with respect to time. Implicitly differentiate the following formulas with respect to time. So that means specifically we're supposed to find the derivative of something with respect to time. State what each rate in the differential equation represents. So we have this formula here, surface area of a sphere. We are going to take the derivative with respect to time, both the left and the right side of the equation. The derivative of A is 1. With respect to time, it's going to be the derivative of A with respect to time. The derivative of 4 pi r squared, keep in mind that pi is a number, I'm going to put the 2 in front, the power rule, that's going to give us 8 pi r. It's the incorrect variable, so then we multiply it by the derivative of r with respect to time. So we have accomplished what we were supposed to accomplish as far as implicitly differentiate with respect to time. State what each rate represents. This rate here represents the rate at which the surface area is changing with respect to time. This rate here is the rate at which the radius is changing with respect to time. You would write that out here in your notes. I'm not going to write it out. Feel free to pause the video and rewind that so that you can write that out properly. Next, we have volume of a sphere. So we're supposed to take the derivative of both sides with respect to time. On the left, the derivative of v with respect to time is dv over dt. On the right, this is the power rule. Multiply the 3 times the front. 3 times 4/3 is 4. And then we have the pi, subtract 1 from the exponent. This is with respect to t, but the variable was an r. So we have to tack on to the end the derivative of r with respect to time. What does this represent? Well, this is the change in the volume with respect to time. This is the rate at which the radius is changing with respect to time. These are both rates. How are they changing with respect to time? Next, we have the Pythagorean Theorem. Solve for one of the legs. Let's say C was the hypotenuse and A and B were legs. Let's take the derivative with respect to time of both the left and right side of the equation. Keep in mind also it tells us C is a constant. So A is a letter, B is a letter, but C is actually a number. So the derivative of A with respect to time is dA over dt. This here is the chain rule. On the right, take the 1/2 and we put it in front. Inside stays the same. Subtract 1 from the exponent. 1/2 minus 1 is the same as 1/2 minus 2 over 2. Gives us an exponent of negative 1/2. Then we have to multiply this by the derivative of the inside. I'm just going to put parentheses, put this derivative in. The derivative of c squared, keep in mind it says that c is a constant. If you square a constant, it's still a constant. Its derivative is going to be 0. There's no variables in this, so we don't have to worry about with respect to time being the incorrect variable. Derivative of b squared is 2b. This is with respect to time. B is not time, so we have to multiply this by the derivative of b with respect to time. could simplify this a little bit. Yeah, I will simplify this a little bit. So this is the change in A with respect to time is equivalent to 2 over the square root of c squared minus b squared over negative 2b times the derivative of b with respect to time. What do the variables represent? Well, this is a rate of change of how A is changing as time is changing. This is a rate of change measuring how B is changing as the time is changing. Volume of a cylinder. This is the same process over and over and over, but the letters don't matter. That's one of the main points of me showing you this is, it doesn't matter what letters we have. If it's the right variable, it's like explicit differentiation. If it's the incorrect variable that you're comparing the denominator of the derivative to, then you add the extra to it, the extra being like the inside of the chain. The other part of this is just to remind you of some of these formulas, like surface area of a sphere, volume of a sphere, Pythagorean theorem, volume of a cylinder, right angle trig, volume of a cone. A lot of those will be given to you on the AP Calculus test, but it would be nice for you to know those things. Volume of a cylinder. Well, if we take the derivative with respect to time, like the directions tell us to the left and right side, let's just be lazy and say this. I was going to say we have to be careful, but we don't because it says r is a constant. If r is a constant, that means the only letters in this are v and h. R is just a number. Derivative of the left side is dv over dt. The right side, we treat this all as a coefficient. Derivative of h is 1, so it's pi r squared times 1. Since we took the derivative with respect to time, and h is clearly not t, we have to put on the end of this derivative of h with respect to time. This is the rate of change. It's comparing how the volume is changing as time is changing. This is a rate of change, comparing the rate at which the height is changing with respect to time. Right angle trig. Cosine of theta is x over 15. It might be better if we write x over 15 as 1/15 x. If we take the derivative of both sides with respect to t, on the left, the derivative of cosine is negative sine. It's the incorrect variable, so we put d theta over dt beside it. Essentially, it's the chain rule that we're just doing there. On the right side, derivative of 1/15 x is 1/15. Also, their incorrect variable. So the derivative of the inside is derivative of x with respect to t. So if we take the derivative with respect to time of both sides of this little fella, gotta be pretty careful on the right side. On the left side, the derivative of v with respect to time is dv over dt. On the right, the reason we got to be careful, when we take this derivative, since it doesn't mention any place here that r or h, that they are constants, this is the product rule. So we take the derivative of this first factor, put the 2 in front, that's going to be 2/3 pi r, subtract 1 from the exponent. It's the incorrect variable, this is an r and this is a t, so we have to multiply it by the derivative of r with respect to t. This is times your second function, or times the second factor. So this is the first, this is the second, plus the first factor times the derivative of the second. The derivative of h is 1. It's the incorrect variable, so we have dh over dt. If you chose not to write this 1, that would be fine. So this is the first times the derivative of the second. Could simplify that a little bit. We could pull some things out to the front. Let's not bother. This is a rate of change, is how the volume is changing as time is changing. This is a rate of change, how the radius is changing as time is changing. This is a rate of change, how the height is changing as time is changing. That concludes the warm-up, just reminding us how to differentiate implicitly. That is video 1 of who knows how many. But go ahead and watch the next one where we do an example of using related rates for circles.